So we got some due Monday here, 14.1, 14.5, and 14.6. So why don't we have a look? All right, now 14.1 is these, they're called the affinity laws. So if you make small adjustments to your impeller size and things, you can use these to figure out what the new condition will be. So what you do is you take what you had and then you multiply it by the ratio of what you've done to the pump. Okay. So what we had here was 2,700 gallons per minute. And what we're going to do is we're going to take that impeller and shave it down a little bit, or maybe get a new one that's a little smaller, which you can do. I mean, pumps have different impellers you can put in them. So what you do, you'd put these different parameters up that you had, and then you would just adjust them. And what you do is you take the ratio of the new to the old. So, you know, we're shaving this impeller down. But then you have to take it to a different power depending on which thing you're adjusting. All right. And then you just multiply it by the old factor, and then that'll make the adjustment for you. Now this only works for small changes. That's all it does. It doesn't work for big changes, just small ones. And now you just run those numbers. So if you've got the flow, you just adjust it by the ratio of the new to the old. If you've got the energy or the feet pressure, you know, whatever you want to think about that, you take it by the square of the ratio. And if you've got horsepower, you take it by the cube of the ratio. And then you just work it out and get the new flow of feet of head and horsepower. Okay, so that's how that works. Yeah, it's pretty straight up. Now, on your calculator, you know, of course, you've got a square button. You may or may not have a cube button. You know, and what you would do on that, I don't know, all calculators work a little differently, but what you would do, I mean, sometimes there's something called an X to the Y button. So what you would do then, you'd take 14 over 14.5. You'd take that, and I'm not even sure what that works out to be. You just take that ratio, and then you go, and then you usually there's a button called X to the Y, and then 3, and then equals. That's normally how that goes.
You can just use a little caret that you might use.
Oh, right, yeah, it might be a caret too, right? Yeah, so, you know, whatever, there's different buttons on different calculators, so, you know, you use whatever you got, you know. All right, so if you do that, you'll get 135, you know, this is how you'd cube something, okay? All right. All right, so that's the first one. That one's pretty straight up. The other two are more complicated. They're doing the whole deal with pumps, you know. So the next two are more complex. So these are 14, 5, and 6, I think.
Are these ones like the ones that we did on 140 and 131?
Yep. Yeah. So you just want to use that as like a model. You know, we got But actually, we got to cover a little bit more before we can do these completely. So let's have a look at a little bit of that new stuff before we get into this too much. All right, so this is on page, it's 143, so I think it is. Yeah, 143. What we want to look at here is power in pumps. So power is a combination of work and time. Okay. Now work is actually a thing from physics. Work is a force applied over a distance. So if you take 30 pounds of water and you lift it 20 feet, what you do is you take the weight of the water times how high you lift it, and you get the work, 600 foot-pounds of work. That's the term for that. Okay. So work is just a weight times a distance that you lift it. Now, you can think of the distance that you're lifting it as like a resistance. So if you lift it 20 feet and you also have 5 feet of head loss pushing it through a pipe as you lift it up, the distance could be considered to be 25 feet. A pump wouldn't know the difference between lift and head loss. It's all just energy loss to a pump, okay? So you take the lift plus the head loss in lifting it. You'd have head loss because when you lift water, normally you're pushing it through a pipe and you'd get head loss for that.
So it'd be similar as if you're trying to lift against gravity, you have to do
Right.
lifted plus gravity against it to actually see.
Yeah, you're looking at the gravitational resistance to lifting something, you know, the gravity's kind of pushes back, so that's why it's harder to lift something. But also as you push it through a pipe, you get that frictional resistance. And the sum of the two is what goes into work, okay? All right, now if you take that times the time it takes to do it, you get what's called the power, okay? So the idea is if you have a little pump, you could lift water up to a reservoir, but it might take a long time. If you've got a very powerful pump, you can do it faster. You can do the same amount of work, but you can do it faster, okay? So power is the ability to do work in a hurry, to do it fast. And if you go way back to the Industrial Revolution, 300 years ago, someone actually measured what a horse could do, because they used, when they were digging coal, this is in England and Wales and Scotland, they got down below the water table and the mines would fill up with water. So they used draft horses to pull the water out of the mine. Okay? This is back before they had pumps. Okay, so somebody, actually it was James Watt, rated a horse. And what he came up with was that a horse could lift something on the order of 1,000 pounds of water 33 feet in 1 minute. Okay? So when he multiplied the lift, the 33 feet times the 1,000 pounds of water, he got 33,000 foot-pounds per minute. And was what he called a horsepower. Okay? And the reason he was doing this was he was selling steam engines that would do the same job. Okay? So if you own a mine and you got a horse, well, you got to have a barn for the horse, you got to feed the horse, you got to take care of the horse, so it all costs money. He's trying to sell steam engines. So he says, well, this steam engine, here's what you got to do to keep it up. It's cheaper than keeping up your horse. See? Yeah, right. Yeah, exactly. You just got to feed it coal. You don't got to put it in a barn or anything like that, Okay, so, and yeah, you can feed it the coal you're digging out of the mountain, basically. Yeah. So, okay, so horsepower is 33,000 foot-pounds per minute. So, my dad got a Corvette when he was in his late 50s, a nice 67 Stingray, and that thing was 327 horsepower, if I remember right. And that is literally like having 327 horses under the hood. I mean, that's the power that went into moving that thing. Okay, that was the idea. All right. So this is how we rate pumps and motors on power. Okay. So pumps deliver power to the water. They give it pressure and make it flow. And the power delivered is a combination of the TDH, which is the total dynamic head. Now that's what that is how high you lift water times plus the head loss, right? That's what TDH is. Multiply that by the flow rate, and you get the rate at which you're moving the water up. Okay? And that will get you the water horsepower, as it's called. Okay. So what you do to find the horsepower is you take the flow rate in gallons per minute, convert that into pounds per minute, multiply that by the TDH. Okay, so now you got the pounds times feet per minute, and then you convert that into horsepower. So if you get that all kind of resolved on the formula sheet there, here's the formula for horsepower. Take the flow in gallons per minute, multiply it by the TDH, the total dynamic head, and the constant you divide it by when you work with that number, and that number is 3,960. So the bottom line from that last little 5 minutes there is to get the horsepower that is delivered to the water, take the flow in gallons per minute, multiply it by the TDH, and divide it by 3,960, and that'll get you the power. Okay, that's basically it. And that's really the main thing you need to remember. You know, that's all you got to do. And that's on the formula sheet. Okay. All right. Now this is the water horsepower, as it's called. Okay, so horsepower is flow times head divided by 3,960. I don't know where that's at on your formula sheet, but that should be on there somewhere. Oh. Yeah, right. Yeah, that's a good one to know. Okay. All right. So if you've got a pump that's pushing 300 gallons per minute against a TDH of 140 feet, or creating a TDH of 140 feet, what water horsepower is required? Okay. So we got 300 gallons per minute times 140 feet, and then you just divide it by 3,960, and that's it. Okay, you're done. That should be in the book. We're just kind of going through the book.
Oh, there it is.
What page are we on now? 143. Okay, thanks.
I like to write down your notes right there, and then when I go back.
Yeah, sure. So, yeah, bottom of page 143. And that gets you at 10.6. So that's the power you got to deliver to the water, so it's called water horsepower. 10.6. Okay. So that's really the thing to remember, is that formula, and it's on your formula sheet. Okay. All right, why don't we find the water horsepower for this pump, the static lift pump that we analyzed earlier. That's the static head pump. Here's the static lift pump. There we go.
have the gallons per minute on that? I can't see.
Yeah, it's on the top. What was it? Was it 1,300? This is the TDH. And I think it was 1,300 gallons per minute. Okay. So 139.36 TDH and 1,300 gallons per minute. So, you know, you could kind of, and you could have carry on with the calculation on this, you know, on this page here and get the water horsepower. Okay. So you can start with those conditions that shown there and then work through to get the water horsepower. And 39.36. And that's all there is to it. You just take the flow rate times the head and divide it by 3960. I mean, that's it.
So the units end up being gallon per minute per foot?
Let's see. So I'm getting 45.7 here. The units, there's conversions in that 3960. And what those do, that those take foot-pounds per minute and convert them into horsepower. So this comes out to be a horsepower number, 45.75. Because that 3960 is has those conversions. It comes from those conversions that were done. So when you do this, you just get water horsepower is what you get. It's got the 8.34 pounds per gallon and the 33,000 foot-pounds per minute per horsepower embedded in it. So it converts everything right to horsepower. Okay. All right. So that's the horsepower that goes to the water. All right. But pumps are machines, all right? And so every step of the way, there's a loss of power. So if you look at the horsepower coming out of the motor, not all of that goes to the water, okay? So the water horsepower is what goes to the water. Coming out of the motor is what's called brake horsepower. And there's an efficiency loss as you go from brake horsepower to water horsepower. It's not a perfectly efficient transfer of power. Machines are never perfectly efficient. Okay. Similarly, there's motor horsepower that goes to the motor. That is not converted by the motor with complete efficiency to brake horsepower. There's power loss. So each step of the way here, there's a bit of power loss, okay? And so you need to know the efficiency of the motor and the efficiency of the pump to kind of work your way down as you go from motor horsepower to brake horsepower to water horsepower. The other thing is that horsepower is used for what comes out of the motor, the brake horsepower, and what goes to the water. Those are horsepowers. But if you look at your electric bill, what you got are kilowatts. That's what you pay for from the electric company. 1 horsepower is 0.746 kilowatts. So we have to do a little bit with units, and we also have to do some things with efficiency to work our way through this system here. Okay. Now, efficiency is what you get out versus what you put in. In this case, you use power out divided by power in. Okay, so if you get 9 horsepower out of a motor, but you put 10 in, that would be 90% efficient. Okay. So every step of the way, the power is decreasing as you go through the system because you got these efficiency losses. Okay, so the brake horsepower is the motor horsepower times the efficiency of the motor, and the water horsepower is the brake horsepower times the efficiency of the pump. Okay, so if you've got 26 motor horsepower that's delivered to the pump, and the motor's 86% efficient, well, that would be 0.86. You make it into a decimal when you're doing these calculations. And the pump is 74% efficient. What's going to happen is you're going to reduce the power to get to your final amount that goes to the water. And see, that's going to be reduced a good bit there. 16.6 horsepower would be delivered to the water. We've got one step down for the motor and a second step down for the pump. Okay. Now, the thing is, though, normally speaking, we go the opposite direction on these calculations. Normally speaking, we know what the water horsepower is because we can calculate it for the system, and we want to step back and get back to what we're going to have to buy from the power company, which is the motor horsepower. So normally we go back the other direction. Okay? Normally we don't start with the motor horsepower and work our way to water horsepower. It's the other way around. We start with the water horsepower and go back to the motor horsepower. So instead of multiplying by these efficiencies, we divide by them. Okay? So if you've got the water horsepower, you can divide it by the efficiency of the pump, and that'll get you the brake horsepower. And then when you got the brake horsepower, you can divide it by the efficiency of the motor and get back to the motor horsepower. And then you can convert that to kilowatts and figure out what it will cost you to run your pumping system. Okay? So that's normally how this works. So you got to step it backwards is how you do it. Because you can calculate the water horsepower. You can calculate that and then walk back. That's how you do that. Okay.
You should have a kilowatt hours going.
Right. You pay for the power, but also the time you use it for. Yeah. So we'll get to that in a minute. Yeah. Looks like you're the one who takes care of the power bill. Huh? Oh, no. Oh, okay. Yeah. Okay, so a pump requires 42 water horsepower. The pump is 79% efficient, and the motor is 86% efficient. Let's see if we can walk our way back to the motor horsepower. Okay. So we got 42 horsepower. That's what's going to the water now. So to figure out what the motor needs to deliver, we divide that by the efficiency of the pump. That'll make that number bigger because we need more power out of the motor that ends up going to the water. And then the same thing, we look at the efficiency of the motor to figure out the power that needs to come into the motor. And you just divide that out, and you get 61.82. So that's the power that needs to come into the motor. Okay. All right. So that's basically how this goes, all right? Now let's say we're drawing 45 motor horsepower. So that's what's going to the motor, and we're running 6 hours a day. And we know that power costs 11 cents, which is $0.11. And as you say there, you buy power by kilowatt hour is what you buy. Okay. And so we got hours to cancel, but we still got motor horsepower we need to convert to kilowatts. So it's 0.746 kilowatts per horsepower. So if we take 45 times 6 times 0.746 to convert that into kilowatt hours, and then if we know that power costs 11 cents a kilowatt hour, we can multiply all that out and we can figure out what this would cost. And when you do that, you should get about $22, okay? So you're going to pay $22.16 a day to run this pump. Now when, we good?
What were I got confused here, where the .746 come from?
That's how you convert from horsepower to kilowatts.
Okay.
Okay.
Oh, I see, okay.
So when power is cheap, people don't worry so much about this, but when power is more expensive, they do. And when the power costs go up, you see high efficiency equipment is pushed more, you know, because you can save power, you know, money you pay for power with that. Now the downside of high efficiency equipment is, as you get more and more efficient, it's harder and harder to maintain. You know, I remember when I bought a furnace, this is quite a few years ago, the fellow selling it to me said, well, you could get a high efficiency furnace, but it's probably not worth it because you're going to have to spend so much maintaining it. You're not going to get it back in the energy you save. So, okay. So that's kind of how that works. All right, why don't you look at that example there on page 146. And why don't you give that a run and see if you can work through that. So this kind of puts all these little different steps that we were just working on together into one problem. So start with the water horsepower, and then get the brake horsepower and the motor horsepower. So the steps on this, so you're going to want the water horsepower, then the brake horsepower and motor horsepower. And then you could get to the kilowatt hours and the cost. That's how you would work through that. So why don't you see if you can do that. A little bit more than 13 water horsepower, you okay with that? Okay. Then get the deficiencies and, or efficiency and divide that out. That'll get you to the motor horsepower, which is the horsepower coming into the motor. It's about 17.3 motor horsepower, something like that. $13.96. It is. All right. I'm not doing too good on my battery, and I don't have my plug-in.
What type of plug-in do you have?
Well, it's an HP. It's got kind of this little jack that fits into the side.
Is it this one? Yours acting up. Oh. Good reflexes.
We're about out of time. So, okay, now, we'll make the homework due Wednesday, I think. Well, should we? We'll just see if we get it in Monday, because, you know, next week's our last week. If you get it in Monday, I can get it back to you Wednesday. So,
I got a question.
Yeah.
Is the final gonna be the accumulation of everything, or just the last part of the game?
the final will not be cumulative. Well, let's see, it'll cover the pumps primarily, okay? And a couple other things. I'll probably have a flow rate problem on there and a force pressure type problem. But all this stuff with pumps, we're using all this other stuff anyway that we've learned. So in a way, it is kind of cumulative because we use it all when we do pumps.
Right.
Okay, but it doesn't go all the way back and cover all that stuff in detail.
I was gonna say, that'd be a lot to,
Yeah,
lot to do.
yeah.
I agree. Right?